All right, so it's time to go ahead and begin. So as you can probably tell from what's on the board, we're going to do a lot of examples today in class, and then you'll have more examples to do for the activity, and it has to do with Carnot maps. And Carnot maps are a technique, it's a pictorial technique to reduce Boolean equations. So on each table, we put this same handout from last week that has the truth table to the logic gates and also laws and identities for Boolean output. And one way that you could reduce Boolean expressions, and again, Boolean just means base 2. So, one way that you can reduce base 2 Boolean equations is just by brute force, follow those rules and identities that's on that handout. And just like in base 10, when you're reducing algebraic equations in base 10, that, you do factoring and like terms and things like that. You can do the same sorts of things in base 2. But Carnot maps, it's a pictorial way of reducing equations. And, out in industry, they don't brute force it. They don't use Carnot maps. They have computer algorithms, programs that will do the reduction of the Boolean equations for you. But I feel, and many other instructors that teach this class, that it's important for students to at least to know, a way of manually doing it. For nothing else, knowing what those algorithms are based on. And of the two, the brute force way of doing it and the Carnot maps, I think Carnot maps for most people is a funner way of doing it. It kind of looks strange at first, but once you get that hang of Carnot maps, a lot of people liken them to crossword puzzles. They actually kind of like doing it. So anyway, that's what today's class is about, Carnot maps. There'll be an activity on it, and then for lab 1, you also will need to do a Carnot map. So you can see the agenda's up there. Now, before we get into Carnot maps, there is one other thing left over from when we were talking about last week, how we can express logic circuits in various different ways, with the truth table, SOP equation, POS equation, diagrams, black box diagram, circuit diagram, all those different methods that we talked about. Well, there's one common error that comes up that I wanted to make sure to go over, just to hopefully prevent it from coming up this quarter, especially on a test. And that often this mistake is made. Sorry for that smudge there. Oh well. That's why I got green. So you can see green. See, often this mistake is made that not A banded with not B is equal to A and B banded all not. See, these are not equal. But a lot of times people make the mistake that they think they are equal. Another way to look at this with the gate symbols is that not A anded with not B. That's when A and B are first knotted before they're anded together. Right? So this NOT gate will invert A, and this NOT gate will invert B, and then these two that have been inverted get anded together. So that's how you end up with not A anded with not B. But to get A, B, A anded with B, then the whole thing knotted, that's the same as a NAND gate. Because remember, a NAND gate, as we said last time, a NAND gate is equal to an AND gate with the output inverted. Right, so the way you get this is first A and B are ANDed together. Then A and B that's been ANDed together, the whole thing is knotted. Okay, so the best way to prove that these aren't equal is to do truth tables for both. Come up with the output F. Sorry, F. do a truth table, figuring out what output F is for this case. And then doing a truth table, figuring out what F is, output F is, for the NAND case. And then you compare truth tables. And if the truth tables are different, right, if you're getting a different output, given the same inputs, well, then they're not equal, right? If you do get the same output, well, then they are equal. So let's go ahead and do the truth table for this case first, the not A and who is not B. So first, each input would be inverted. So this 0, 0 would become 1, 1. This 0, 1 would become 1, 0. 1, 0 would become 0, 1. These 2, 1, 0. And then to get the output, not A and not B, they're ANDed together. So when is output F here going to be a 1? Given that not A and not B are the input to this AND. But when do you get a 1 out of an AND? When both what are 1? Yeah, when all inputs are 1 to an AND gate, you get a 1 out. So you see, we would get a 1 out here, right? And then all the rest would be 0. Right? Remember the AND gate from last time? Okay, so that's the truth table for this case. Not A and it would not be. Okay, let's do the truth table for the NAND gate. And we're using this equivalency here, right? The NAND gate's equal to an AND with an inverted output. So first, when you AND A and B together, so we'll only get a 1 here. Again, you only get a 1 out of an AND gate when all the inputs are 1. And then that output A and B is going to get inverted. So this column here gets inverted. So we'll have 1, 1, 1, 0. So now if you compare output F of the NAND gate to output F of not A and it would not B, you can see they're not the same. Right? So you see they're not equal. That's just a proof that these are not equal. Okay. See where this comes up, and this is what I'm hoping doesn't happen this quarter. See where this situation comes up quite often is, remember last time we were taking from a truth table, we were writing SOP equations, and we would write the term. You know, we would write the term where if there was a 1, we just put that variable. If there was a 0, we put not that variable. So for example, if this term was part of one of our SOP equations like we were doing last time, we would have A, not B, not C. But you see what people do sometimes is they do this. You see, that's incorrect. See, sometimes they make this error because they think that, you know, not a variable ANDed with not a variable is equal to those two variables all ANDed with or all not. If you just said it's true. The other error that can be made that comes up with the same situation is someone's just kind of sloppy, you know, when they're writing the bars over the variables, they just kind of put them together inadvertently because they're not careful. Okay, but whether it's you're not being careful or whether it's you think they're equal on a test, they're both equally wrong. All right, so you want to be careful you don't make that mistake. Okay, like I said, it's a very common error that people make. Most of the time, it's just because they're going too fast and the bars just become one instead of two separate ones. Okay. All right. So, this doesn't have anything to do with Carnot. This was something kind of left over from last time. I just wanted to make sure that people are cautious. All right. So any questions up to this point? Does this all make sense? Anytime you want to see if two expressions are equal, you can always do this. You can always make a truth table for both the expressions and see whether you end up with the same truth table. Right? If you do, they're equal. If you don't, they're not equal. Okay. All right. So now let's talk about Carnot maps, or K maps for short. And like I said, Carnot maps are used to come up with reduced Boolean equations. So the first thing is there's two Carnot maps that we go over in this class. There's an 8-cell. Okay, each square is called a cell. Okay, so 8-cell and a 16-cell. So the first thing is notice the numbering. Right, for this 8 cell, notice it goes 0, 1, 3, 2, 4, 5, 7. See, they don't go in order. And that's not a mistake. That's how it should. Also, if you look at the 16 cell, the top 2 rows are just like the 2 rows of the 8 cell. But then the third row starts with 12, 13, 15, 14, and then the last row is 8, 9, 11, 10. Okay. So the first thing that usually people wonder about when they first look at a kernel map is why is the numbering like that? You know, why isn't it just 0, 1, 2, 3, 4, 5, 6, 7? Like, you know, why isn't the numbering in order? Why is it not in order? Well, the reason why the kernel map has the numbering that you see is so that it has this property called adjacency. Okay, adjacency. I can't remember how to spell it. Adjacency. And what we mean by adjacency in this aspect is that when we have the numbering, as you see here, if you look at any cell and compare that binary number, that cell, to any cell that is to the side of it or below it or above it, you will see that the binary numbers for those cells only differ by 1 bit. So for example, if we look at the 0 cell here, okay, 0 in binary is all zeros that you know. Well, if I then compare 0 to binary 1, see there's only a 1 bit difference between 0 and binary 1. Okay, also if I compare 0 to 4, 0 to 4, also there's only a 1 bit difference. And you can do this for any of the cells side by side or up down. So like for example, we look at 3, cell 3. Okay, here's a binary 3. I compare it to binary 1. See, there's only a 1 bit difference. If I compare 3 and 2, again, 1 bit difference. If I compare 3 and 7, only a 1 bit difference. See, if we had put the numbers in order, that wouldn't be true. There would be cells where when you looked either to the side or up down, there would be more than a 1 bit difference. And when you have more than a 1 bit difference, you don't have this property of adjacency. And if you don't have the property of adjacency, kernel maps are not going to work for what we use them for, which is reducing equations. See, they only work because of this property of adjacency. Okay, and the same thing is true for the 16 cell. You take any cell of a 16 cell and you look above or below or to the side, you're going to see a 1 bit difference based on this number. Now, if you go diagonal, you're likely to see more than a 1 bit difference. Okay, diagonal doesn't matter. It's side by side, up, down, that has to be a 1 bit difference for this to work. Okay? All right, so any questions about the numbering? Okay, now the next thing is notice for the 8 cell, notice that this row we have variable A. And then for these 2 columns, we have variable B. And then for these 2 middle columns, we have variable C. Well, the reason you see the variables like that is because this row where we have variable A, 4, 5, 6, and 7. Right, so 4, 5, 6, and 7. See, A is equal to 1. You likewise could do this. You likewise could put not A next to this row, right? Because for this row, 0, 1, 2, and 3, A equals 0 for all those numbers, binary numbers. Okay. B, these 2 columns, 2, 3, 6, 7. If you look here at the truth table, 2, 3, 6, 7, B equals 1. Likewise, you could put not B for these 2 columns, because for 0, 1, 4, 5, 0, 1, 4, 5, B is equal to 0. Okay, C is for these 2 middle columns, because if you look at 1, 3, 5, 7, C is 1. Likewise, this column and this column could be not C. Okay, because for 0, 4, 2, 6, 0, 4, 4, 0, 2, 4, 6. That bit here. Okay. So do you see how we get these? Now, most often you'll either see A, B, C, and it's understood where the knots are. Or sometimes people put the knots, like some people put not A, not B, not C, and it's understood where the ones without the knot are. Okay, usually you don't see both of them, you see one of them. Okay, and it's the same idea for a 16 cell. For a 16 cell, these two rows, we have A because if you look at 8, 9, 10, 11, 12, 13, 15, 14, right? A is equal to 1. And for these two rows, not A. These two rows here would be not C. This row here would be not B. This would be not B. This column here would be not E. So does everybody see how we get, that these two rows are A, why these two rows are B, these two rows C, these two rows D, and so on? Okay. All right. So no questions up to this point?
Did you have to manually figure out which one's A and A not, or C and C not, or is it like the same format for each single?
Well, each 8-cell Carnot map is gonna have, its variables determined the same way. Now, you'll see this in activity. You could have a Carnot map that is drawn like vertically instead of horizontally, but no matter how it's drawn, it's always true that wherever the A is, it means those cells have A equal to 1, and so on.
I mean, did you have to, because did you have to have, I think in order to do that, for each cell to know the binary number, that you have to do it for each cell.
Well, yeah, each cell, this number, which is called an index, corresponds to an input. And then, maybe this will help with your question. Then, for each input, we're going to have some output value, right? So, for example, I'm just making up output values here, but, this could be a 1, this could be a 0, maybe we have something like this. Well, now, inside each cell goes the output value for that input value. So, index 0, which is input 0, output is 1. So you see I put a 1 there. Right, and then cell 1, which is index 1, which is input 1, well, output for that input is 0. So you see inside each cell goes the output corresponding to that input index. So you see this would be 0, this would be 0, this would be 0, this would be 1. It's the same idea for a 16 cell. Whatever these, oops, we won't do that yet. That's coming up later. Right, a 1 would go here, a 0 here, a 0 here, a 1 here, a 1 here, and so on. Right, so the cells contain the output for that input. Okay, that help? Okay. So now, this is just some basics, okay, of Carnot maps. Now we're going to see how we actually use Carnot maps to get a reduced expression. So the goal, again, of using Carnot maps is most reduced Boolean equation. Okay, and in order to get the most reduced Boolean equation from a Carnot map, you'll see what we want to accomplish is we want to get the least number of largest groupings. Okay, and we're going to talk about what groupings are coming up. And once we start doing some of these examples, I think you'll understand why, in order to get the most reduced Boolean expression from a Carnot map, you want the least number of largest groupings. Now, these groupings have to be either square or rectangular. Okay, you can't have like odd shaped groupings, you can't have like diagonal groupings. Okay, it's either square or rectangular. Also, the groupings have to either be 1, 2, 4, 8, if you have an 8 cell. If you have a 16 cell, they have to be either 1, 2, 4, 8, or 16. Okay. If you have an 8 cell, and you have a grouping of 1, that's going to give you a 3 variable term. If you have an 8 cell and you have a 2 grouping, that's going to give you a 2 variable term. 8 cell 4 grouping will give you 1 variable term. If you have an 8 cell and you have a grouping of 8, meaning that all the outputs are either equal to 1 or all the outputs are equal to 0, because you can group either 1s or 0s, and we're going to do examples of both. Well, if all your outputs for all your inputs is equal to 1, that means your output is just 1. So you see, if you have a grouping of 8, the answer is either going to be 1 if you're grouping 1s, or 0 if you're grouping 0s. And then, of course, you can't have a 16 grouping with an 8 cell because you don't have enough cells. So this would, not apply to an 8 cell. Okay, now if you have a 16 cell and it's a group of 1, that's a 4 variable term. Group of 2 with the 16 cell is 3 variable. 16 cell with a 4 grouping is a 2 variable. 16 cell with an 8 grouping is a 1 variable. And if you have a 16 cell and all the outputs are 1 or all the outputs are 0, well then it's just 1 or 0, depending on what you're grouping. Okay, now you'll see why it's like this coming up with these examples, but this is how many variables you get based on the number of groupings. Or, well, not the number of groupings, but how many 1s or 0s you have in a group.
So this is when you have the group of X, if you take the biggest group in it, or is it?
Yeah, you want to start, you always want to start with looking for the largest group possible, because the largest group is going to give you the least number of variables. And then you want the least number of the largest groups, because the least number of groups give you the least terms. Right? So the least number gives you the least terms. The larger the group gives you the lesser variables. And you'll see as we do some of these examples. Okay, in fact, let's do this first example, this one right here, this 8 cell. And we're grouping 1s. Okay, so when you're looking at this, you just go in order. You go, okay, can I group 8? Well, there's no way to group 8 because I only have 3 1s. Okay. Then you go, okay, can I make a group of 4? Well, it's not possible to do a group of 4 because again, there's only 3 1s. Okay, but how about a group of 2? Do you see a group of 2 that can be either a square or a rectangle? Where is it? Where's our group of 2 in here? Yeah, these 2 cells here, 0 and 4. See, I can group those. That's a group of 2 1. Okay, now to get the term, right? See, it's going to give us a 2 variable term. To get the term that grouping gives us, you look at what is common to that 2 grouping. So you see this 2 grouping, it's in the same column here. And what's this column? These 2 columns over here are B. So what's these 2 columns? 2 columns. Right. See, that's not. So you see this 2 group here is both in. Oh, when I put minus B for it, not B. Sorry. Right. So that's common. What else is common? Not C. Right. Because not C are these 2 columns. So you see the term I would get. And up here is my output. The term I would get from these, this 2 grouping is not B, not C. See, A is not in this term because A changes in that 2 grouping, right? Because this one is in not A row, and this one is in A row. So any variable that changes, that drops out. Okay, the variables that are common to the group, that's what remains. Right, so does everybody see how I got not B, not C? Now, you could also write not C, not B, because you know, in Boolean algebra, just like in base 2, you know, the variables can be interchanged. But by convention, and also to make grading easier, please put your terms in alphabetical order. Okay, so even though not C, not B is also correct, just for ease of grading, and also it's just done by convention, you know, put it as not B, not C, put it in alphabetical order. Okay. All right, but we're not done because we haven't covered all the ones yet. We still have this one over here. And you see, I can't group that one with anything else. Okay, it's all by itself. So this is just going to be a group of 1. And when you have a group of 1 and it's an 8 cell, it's 3 variables. And this is just going to be the term that gives us a binary 3. So our reduced expression F for F would be not B, not C, or what we get from this grouping, which is just going to be not A, B, C, right? Because that's a binary 3, right? 0, 1, 1. Okay, so does everybody see how we get that? All right, move on to the next one. No questions on this one. By the way, all these examples, I didn't pick these like haphazardly. I picked these because each one shows something, you know, shows something that's useful to know. Okay, this was just kind of a basic starting point, but you'll see as we go along, there's certain peculiarities of this, you know, when you're doing K-maps, and I tried to cover most, if not all of them. All right, so let's move to this one. Okay, so again, we're grouping ones. Again, can't group 8, only have 4 ones. Now, here's something, and it's the reason why I picked this example, that you need to know about Carnot maps, and that's the edges touch. So instead of doing two group grouping, I could do 1 4 group grouping because these edges touch. So you see, I can group 2 and 6 with 0 and 4. And you see, by doing a 4 grouping, I'm just going to have 1 term that's 1 variable. See, if I had done two groupings, I would have 2 terms, and each term would have 2 variables. Right? That's not the most reduced. So you see how if you have the least number of groupings, that gives you the least number of terms. And if you have the largest of groupings, that gives you the least number of variables. Okay, so this 4 grouping is going to give us a 1 variable term. So what variable is common to this 4 grouping? Not C. Okay. Right, see the 4 groupings and not C. See, A changes, B changes, but C is common to that 4 grouping. Right, so everybody see how I got not C here? Okay, ready for the next one? All right, let's look at this one. Okay, we're still grouping ones. So what would you group first? Again, remember, you want the fewest, largest groupings. Yeah, there's a 4 grouping. What cells? 1, 3, 5, 7, right? Here's a 4 grouping right here. So what term is that going to give us? What's common to this 4 groupings? C, just C. Okay, so now we just have to account for this other one. Now, here's another thing you can do, and this is the reason why I have this example. Groups can overlap. So instead of just doing a single group of 1, which would give me a term with 3 variables, I would group this with this one and make a 2 group. You see, I can overlap. If by overlapping, I'm going to get a more reduced equation, right? Because a 2 grouping gives me a term with 2 variables, right? If I did a single grouping, that would be a term with 3 variables, which is not as reduced, right? So you can overlap, groups can overlap. Okay, so this is going to give us a 2-term variable or 2 variable term. Okay. So what is it going to do? What's common to this 2 grouping? AB. AB? Okay, any questions on that one? The big thing on that, again, is you can overlap groups. All right, now let's group zeros, okay, because you know, you can group ones, you can group zeros. When you group zeros, you're gonna get the SOP for not X. And when you group ones, you get SOP for F. When you group zeros, you get SOP for not F, right? That's no different than if you're going from a truth table, right? From a truth table, if you look at the ones, you get SOP for F, right? If you look at the zeros, you get SOP for not F. The difference is when you go from a truth table, that's the non-reduced equation, right? But when you use a K-map, you're getting the reduced equations. All right, so what would you do here? What would you do for grouping? We're looking at zeros now. Do you think we can do this for group? No, why not? Yeah, it's gotta be a square or rectangle. You can't have a regular shape. See, that's not a square or rectangle, so you can't do a group of 4. So you have to do groups of what? 2. So which group of 2 do you do? You want to do this 0 and 1? Okay, do 0 and 1. Okay, so that's going to give us a 2 variable term, and what is it going to be? What's common to these 2? What is it? Not A, not B. Right? Everybody agree? Not A, not B. Right? It's C that changes, right? Because here the 0 is C, in column C. Here this is not C, so C drops out. Okay, what do you want to do next? 5 and 7, okay. Okay, so what is common to this 2 grouping here? A and C. Okay, now what would you do with this one here? Now remember, edges touch. 2 and 0, right? Because again, if I just did a single, that's going to give me a 3 variable term. But if I overlap it, right, because edges touch, I'll get a 2 variable term with the 2 grouping. You always got to be thinking that you want the most reduced. Okay, and then what is common to these 2? Not A, not C. Yeah. Now, can you see that this one actually has more than one correct answer? Do you see that? Because how else could have we grouped this? Yeah, we could have kept those the same, but then did this group 1 and 5, right? So you see, this particular Carnot map has more than one correct reduced solution, depending on how you did your grouping. So sometimes that happens. Sometimes you'll have a Carnot map where there's more than one correct solution.
Could you group 0, 1, and 2?
No, because the groups have to be powers of 2. Yeah, you can't have like a group of 3 or 5 or 6 or anything like that. It's got to be 1, 2, 4, 8, and then if you're doing 16, you can do 16. Okay, so is everybody all right with this one? All right, the next one got a symbol that you haven't seen before. We're back to grouping 1s, but what haven't you seen before? Which symbol? Yeah, this dash, right? We haven't seen a dash before. Okay, this dash indicates what we call a don't care. Okay, sometimes called a doesn't matter. Okay, irrelevant. Any of those. See, in any digital type circuit, digital type system, you only have 2 possible values of output. It's either going to be 0, which is typically 0 volts, or 1, which is typically a plus amount of voltage. But you may have a case where you have an output and you don't care whether it's a 0 or 1. Like the most common example of an output that's a don't care is an output that's not connected to anything. Sometimes, and you'll see in this class that we have at least one design where we have an output that we don't connect anything because we're not using. Okay, so, a lot of times you'll have devices that have more than one output. And for whatever reason, you're not using all the outputs. Okay, so if you're not using an output, that's a don't care. So in kernel maps, don't cares are like wildcards. You make the don't care equal to whatever's going to lead to the most reduced expression. So you can make a don't care equal to 0 if it's going to help you do that, or you can make a don't care equal to a 1 if it's going to help you get to the most reduced expression. Okay, so you get to choose what the don't care is equal to. So we're doing this K-map here, and again, we're grouping 1. So what would you make these don't cares equal to get the most reduced expression for this K-map? Like, what would you make this don't care equal to? 1. Why would you make it a 1? I would. Why? Right. By making this a 1, I can now do 1 for grouping, as opposed to if that was a 0, I'd have 2 groupings. 1 for grouping is going to give me less, right? It's just going to give me a single term, single variable term, as opposed to two variable terms. Okay. How about this don't care over here? 0. Yeah, just make it a 0. Right? Because if I made that a 1, I'd have to add another term, maybe group it with over here, but that adds a whole nother term. So you see, by making this don't care a 1 and that don't care a 0, I just end up with a single variable term, right? One term that's a single variable. What variable am I going to get here? Not D. Okay, so see, that's an example of taking advantage of don't cares. All right, we got another example with some don't cares, and here we're grouping zeros. Okay, so again, when you group zeros, you're going to get SOP for nada, reduced expression, SOP for nada. So what would you make those don't cares equal to? We're grouping zeros. What would you do? 1s. Yeah, why? Because then you have to go into 0. So. Yeah, if I make any of these don't care 0, I'm just going to add terms, right? If I make all these don't cares 1, I just have this 1, 2 grouping. Right? If I made this a 0, I'd add a term, make that a 0. Any of these, if I made 0, I'd add terms. I did this one on purpose because, sometimes, I don't know, it's almost, I think, psychological or something. Like, people feel as though you got to use the don't care. Like, it's got to be, and sometimes you want your don't cares not to be part of your groups, right? If it's going to lead to the most reduced expression. So, what term are we going to get? A naught C. A naught C, exactly. Right? Because A naught's common and C's B changes, so that drops out. Right. So those are all the 8-cell examples. And see, if you understood the 8-cell, the only difference with the 16-cell, that group of 1 gives you 4 variables, group of 2, 3, group of 4, 2, group of 8, 1. That's the only difference. The rest of it's the same. The concept's the same. And the approach is the same. Okay, so let's look at this one. We're grouping 1. Can't be groups of 8 because we only have 5 ones. Do we have a group of 4? Yeah, we do, because remember, edges touch. So you see, I can group 4 and the 12, the 6 and the 14. See, this is a 4 grouping, but again, edges touch. So a 4 grouping in a 16-cell gives you 2 variables. So what 2 variables are common to this 4 grouping? Say B, I heard B. B, what else is common? Not D, right? So remember, not D is here. All right, so that takes care of those 4 ones. How would you take care of this one? Yeah, group it with the 4, right? Overlap. I mean, how many variables is this term gonna have? This is a 16 cell, it's gonna be a 3 variable. So what 3 variables are common to this? Not A, B, not C, right? Right, not, it's in the not A row, it's in the not, or excuse me, not A row, not A row, B row, and not C column. D changes, right? Because this one is in D and this one's in not, so D drops out. Okay, so any questions on that one? All right, let's come up to this one. Again, we're grouping ones. Could you do this? Could you do a group of 8 like that? No, okay, that's not a square or rectangle.
With the top one on the last one.
Say that again, the top.
The last problem.
Oh, we're going back to here.
Yeah.
Oh, I forgot this one. Thank you. I'm sorry. I got so excited, I forgot this one. Yeah, what do we have to do with this one? Do we group it with anything? No, it's just a single group. So, yeah, I apologize. I missed that. Thank you for pointing that out. So what's the term? Yeah, it's gonna be a 3 in binary with 4 bits. So what would I write here? Not A, not B, not B, C, then what? E, that, yeah, 0, 0, 1, 1, which is 3 in binary with 4 bits. Okay. Yeah, sorry again for missing that. All right, now we can look at this. Okay, again, we wouldn't group these 8 because that's in a regular shape. It has to be either a square or rectangle. It can't be something that's not square or rectangle. Okay, so what would you do for this one? Which ones? Yep, we could do this 4 grouping. Okay, and that's gonna give us a 2 variable term, right? 4 grouping for 16 cells. What is it? 4 grouping for 16 cells gives you 2 variables. So what 2 variables are the same for this grouping here? B and D, right? Same row B, same column. All right, what do you want to do next? So this bottom 4 here, that overlaps. Yeah, okay, that's good. So yeah, 13, 15, 9, 11. So what 2 variables are common to this 4 grouping? A, B. Okay, so now we got these 2 to account for. What would you do next? Yeah, the whole row, right? The whole row. 12, 13, 15, 14. So what's common to this row? What is it? AB. So you see that would be the reduced for F. Okay, let's let's do this one. Okay, now this one brings up something that's good to know. And that's when you have a 16 cell like this, the corners touch. So you see how we have, if we're grouping ones, you see how we have a 1 in this corner, 1 in that corner, 1 in that corner, 1 in that corner? Well, that's a 4 grouping because the corners touch. So I can group all these ones together in the corner. And what's common to the corners? What's common to these corners here? Say that again? Not B, not D. See that the corners are in row not B and also in column not D. And see the corners would give us not B, not D. Okay, now we have a don't care. So what would you make this don't care equal to? Yeah, make it a 1, because then we can do a 4 grouping here in the middle. And we did a 4 grouping in the middle here, and it gave us BD, right? So this would be BD. Now, just as a little preview, we could actually reduce this further, not using a Carnot map, but by using a Boolean identity that we're going to talk about next week. Okay, because there's 2 gates we haven't talked about yet that are called compound gates because they're made out of the basic gates that we covered. You know, they're not the and, the or, the and, and the or. Those 5 gates are called basic gates, but there's 2 other gates, exclusive or and exclusive nor, that we'll talk about next week. And when we do, you'll see that we could actually go 1 step further. Okay, but for what we know now, this would be the most reduced. Okay, 1 more to go, and then you'll be ready for the activity. And that's this one here. Here we're going to group zeros. So since we're grouping zeros, we're going to get not F. We got some don't cares. So what would you do in this problem? Yeah, we got a 4 grouping here. And what term are we going to get? What's common to this column? Not C, not D. Okay, now we got some don't care. Oh, we got another 0 here. We also have some don't cares. What would you do? What would you do with this 0? It's on the edge, so. Yeah, you can group it with the 8, right? Yeah, so you can group this 0 and the 10 index with this 0 and the 8 index. And that's going to give us a 3 variable term, right? And what are the 3 variables going to be? It's going to give us A, not E, what's the other? We need 1 more term, not D, and what's the other? Not B, right? Does everybody agree? Because C changes, right? Because C, this 0 is in the C column and this 0 is in the not C. So C drops out, but we're left with that. So does everybody agree with that? Okay, so think about last class. Last class, we talked about SOP and POS. And remember how last class we said you can easily go from a truth table to SOP for F or SOP for not F, right? To get SOP for F from a truth table, you just look at where the 1s are, right? The 1 outputs. And to get not F, SOP from a truth table, you look where the 0s are. Well, in a K-map, to get the reduced SOP for F, you look where the 1s are. To get the reduced SOP for not F, you look where the 0s are. Now, what if, you know, thinking back to last class, what if we wanted POS for F? Right, product of sums for F, what would we have to start with? SOP for not F. Same thing with a Carnot map. See, if I want the reduced POS for F, if I want reduced POS for F, you start with reduced SOP for F. Right? The only difference when you're going from a truth table, it's not the most reduced, right? It's non-reduced. But when you're going from a K-map, it's just reduced, but it's the same thought process. So now, what would I do to this SOP for not F to get POS for F? And what did we do last class? Invert everything. And what else? You all forgotten already. What did you do last? Oh, there we go. Yeah. Yeah, it's everything gets inverted, ands to ors to ands, right? So you see this gets inverted to F, and then we're gonna have C ORed with E, ANDed with not A, ORed with B, ORed with B. So I always double check that it's easy to forget something. So I inverted all of them. I changed these ands to ors and I changed that or to. Okay, so to go from reduced SOP to reduced POS, it's the same, you're doing De Morgan's twice, right? Just like when we did the non-reduced cases, when we're doing the truth tables last. Okay, so do you have any questions up to this point about any of the examples? Because the activity that I have for you today, it's practicing this. I have like 12 for you to practice. Okay. Now, in that activity, there's two forms that are talked about or that are given. One is compact minimum form, and the other one is compact maximum form. And they look complicated, but actually, it's very easy to use them. So there's an ant, right? So let's first look at compact minimum form. So you can see that this form has a summation sign, and it's got some numbers in the parentheses. Well, these numbers are the indexes. And again, when I say index, I'm talking about the number that's in the cell of a primary. Okay. Compact minimum form, these numbers are the indexes for when F equals 1 and the output equals 1. Right, so we have our 8 cell. Say this is an 8 cell. 0, 1, 3, 2, 4, 5, 7, 6. Well, this tells us that there's a 1 there, there's a 1 there, there's a 1 there, and there's a 1 there, and that means the other ones have to be 0. Okay, so it's just a shorthand to let you know which outputs of a Carnot map are equal to 1 and 0 for that map. Okay, compact maximum form, and you see the difference here is this Greek symbol. Here's the summation, here's the capital pi, whatever you call that, in Greek alphabet. But it's the same idea that these are indexes. But when you have the compact maximum form, these indexes are for when F equals 0. Right, so you would put zeros in those cells. Okay. All right, so the only thing left before you can start work today is I just want to show you the activity on Canvas, and I also want to show you lab 1. And I want to remind you of these things here. So let me do the reminders first before we pull down the screen. I show you the activity in the lab. I've talked about this already, but I got some emails, since last time. So I just want to make sure that we're all on the same page. First of all, like I've said, for the lab work, and also when you do the activity, every student's doing their own thing. So, for the lab work, you're all doing your own design. Again, I don't want to see people sitting side by side, either looking, one person looking over another person's shoulder, watching what the other person's doing, or you're sitting side by side and you're typing in the same thing. Okay, the idea is to learn from each other, and you can't do that if you're doing the same thing or you're not doing anything at all yourself. Again, you're looking over somebody's shoulder. So again, when you're in your groups for the lab work, sit across from each other or sit in different parts of the room, do your own thing, and then you can help each other, because if you run into a problem, you can go to your lab partner and maybe figure out what it is, right? Because since you're doing different things, maybe that person is having success with something you're not, and you can compare and say, oh, I forgot this semicolon or whatever it might have been, because most of the time it's some syntax error or something like that. Something that you just forgot or did. Okay, and then also, again, it's one lab submission per group. So I've told the graders that if both people in a group submit, the lab work, I've told the graders just to randomly choose one and just grade one and put a comment telling the people that in the future, it's only one submission per group. And the reason for this, and even though I didn't make a requirement, so if you don't do this, points won't be taken off, but I strongly urge you to do this, even though it's not required. And that's when you make the video, have both people there. Don't just rely on one person. The reason to have both people there is because if you have both people there, it's less likely you'll forget something. Like it's less likely you'll only do 7 of the 8 rows instead of all 8. Because if you don't do all the rows in the truth table when you're doing the video, then the grader can't determine whether that design's working 100% or not. And again, you only got one shot. There's only one chance to turn it in, but make sure it's correct the first time you turn it in. Okay? And then again, remember, you just submit one PDF, right? You should have a link to the demo video, put your video on YouTube or Google Drive or some other place where you can link to. And then these 3 screenshots. Okay. Also, on the screenshots, just have screenshots of the warnings. Okay, a person, I don't think it was this section, I think it was a different section, but somebody sent me a screenshot of their warnings and they included the information. So when they sent the email, they had like maybe 6 warnings and 130 information. So when they sent the screenshot, it was like 12 screenshots because they were showing all the information in addition to the warnings. You don't have to show the information ones. There's like a little checkbox. Just uncheck that box and it'll just be the warnings. Okay. All right. So like I said, just one more thing and you can start working in your groups. Let me show you what's on Canvas for the activity as well as the lab. Take a minute for it to run here. Okay, so here's the activity. So you can see there's 8 Carnot maps. I want you to do reduced SOP. So reduced SOP, that's when you're circling the ones for all 8. And then I also want you to do the reduced POS for F for just these 4 on the right. So since you want reduced POS for F, that means you want to circle what? Zeros, right? Because circling the zeros will give you the reduced SOP for not F, right? So when you do the Morgans twice, you'll get the reduced POS for F. Okay, so basically there's 12 problems. 8, you're doing reduced SOP. These 4 reduced POS.
Wait, and you know that whether to do SOP or POS depending on if it's the sum or the product, right? Is that how you can tell?
No, that's a good question. These compact min forms don't have anything to do with what reduced expression you want. All these tell us is this tells us what cells have 1s, so therefore what's not here has 0s. And this just tells us where the 0s are. But after you put in the 0s and the 1s based on this, you can either group 1s or 0s, and same thing here. So yeah, the compact min forms don't have anything to do with what expression you want to get. Right? They just tell you where the 0s
So
come
it's just an easy way of representing the table.
Exactly.
Right.
Yeah, instead of writing a truth table, yeah, you can do it. That's why it's called compact.
Yeah.
Yeah. Yeah. Okay. Right. So but now my answers for the activity are up here on the wall, so you can take a picture when you're ready. Okay, last thing is I just want to show you the lab 1, and this is also on Canvas. It's under the lab section under modules. But here's lab 1. So this isn't due until Monday of next week. But you'll be able to do quite a bit of it, not all of it, because some of what you need to do lab 1 we'll talk about on Thursday. But you can do part 1 of lab 1. So you're given this problem statement that there's a lockbox that has 4 inputs. And the lockbox will open when the output is 1, and it opens for these input combinations. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 input combinations that will open the lockbox where the output is 1. So therefore, the other combinations, the output is 0. So we have 4 inputs. So if you have 4 inputs, how many possible unique combinations of zeros and ones can we have at the input? 16, right? 2 to the 4, 16. So you're going to have a truth table with 16 rows. And for these combinations, the output is 1. For the combinations not shown, the output is 0. So draw that truth table. Then from the truth table, get the SOP and POS expressions. Those will be your non-reduced expressions. Then draw a black box. And I got a lot of questions about this in my earlier section today. We talked about a black box last week. I mean, granted, it was briefly because it didn't really require a lot of time to talk about. But who can tell me what a black box diagram is?
It's like when you don't care about the implementation, you just look at it's like, you just look at it and say, oh, that works. So it's like just the module.
Anyone else can add to that?
Just like show me what's-
Yeah, I mean, you're correct, but that's the main thing is that the black box diagram, it's showing your main inputs and your main outputs. So for lab 0, you had 3 inputs and you just had 1 output. For lab 1, you're going to have 4 inputs and you're going to have 2 outputs because we want you to use a K-map or K-maps to find the reduced SOP and the reduced POS. So your black box diagram, it's going to have 4 inputs coming in. It's going to have 2 outputs coming out. One output's going to be your SOP output. The other output is going to be your POS output. Okay. So after you do this preliminary work, then you go into Vivado and you follow the same process that you did for lab 0. You know, you'll have to define your inputs and outputs. That's where your black box diagram is really handy, right? Because your black box diagram shows you what the inputs and outputs are. Okay, and then for lab 0, you just had 1 Boolean expression, right? You did assign F to your Boolean expression. Here in your design source file, you're going to have 2 assigned statements, 1 for the SOP reduced and 1 for the POS reduced. Also remember, and I mentioned this in my video, but again, some people in my earlier section seem to have forgotten this. Be descriptive with your inputs and outputs. Don't just use ABC. You know, be descriptive. Like in my video for the intro video, remember I used FLC for first logic circuit. Then I put like _A. You can do something similar, but don't just use ABC. You know, be more descriptive. Also, since you have 2 outputs, maybe call one of them, you know, like F_SOP and the other one F_POS. Okay. So when you go through your truth table for the, when you're in Vivado and, you know, you've done all your design source, you know, you put in your assigned statement for the equations, and then you go to simulate and you look at your timing diagram in Vivado and you've got an output SOP and an output POS. Should those outputs be the same? Right. Yeah. These different form of equations, they come from the same truth table. They come from the same K-map. So you should get the same output for both forms. Now, you don't have to download anything to the board today because part 2 in Thursday's class is going to be about this. Part 2 is adding another output that's called a NOR output. Okay, and on Thursday, we're going to talk about what NOR is and also what NAND is. So if you, by next class, if you can get a good simulation on Vivado for SOP and POS, Thursday, you'll only have to do just a little bit more to finish this. You basically just have to add one more line, one more equation in your design source and, you know, run a simulation again, and then you'll be ready to download to the board. So you're not going to download anything to the board until after Thursday. Okay, the goal is to get a good simulation for SOP and POS by Thursday if you can. You know, if you don't, that's fine because you'll have more time, of course. It's not due till Monday. I'm just saying if you do that, you know, I would think you definitely would finish on Thursday. Okay? So do you have any questions, before you get started? Because,
When we're turning in our labs, we only have to include like the warnings and the like schematic, not actual code for it, right?
right, yeah, again. for any lab, yeah, it's these 4 things. So in one PDF, you want to link to the demo video, then screenshot of the simulation timing diagrams, screenshot of warnings, screenshot of the design schematic. Now, this is a long way off, and I'll talk more about it when we get closer, but for the final projects, there'll be more that's required. But, I'll talk about that when we get closer. Okay, any other questions before you get started? Because, the next thing to do is to do the activity as your group at a table. Then once you're done with the activity, make sure each table passes in a hard copy so you get credit for it. And then once you get to the lab part, you can either stay here and work on it, or if you want to leave and work on it somewhere else, that's fine. Okay, but you have to stay and do the activity here and pass it in before you, and your table has to pass it in before somebody goes. I don't want to see somebody leaving their group before their group is done with the activity. You won't get credit if that happens. You won't get credit for the activity. Okay? All right, and Ethan will be here around 2 o'clock also to assist if you need assistance.